In this second class of the automotive air conditioning course, we will focus on the evaporator, also known as the interior coil of the system. This component is essential within the vehicle's refrigeration circuit because it performs the fundamental task of absorbing the heat coming from the cabin. Understanding its operation, characteristics, and possible failures allows the technician to diagnose any problem related to the vehicle's internal climate control with greater precision. The evaporator is installed inside the vehicle's dashboard or in an adjacent box specifically designed to house the system components. Its location makes it easier for the interior air to be efficiently directed toward the coil to be cooled. At this stage of the circuit, the refrigerant circulates at low pressure because the compressor is responsible for suctioning the gas coming from this area, maintaining a continuous flow that allows the necessary heat transfer for cooling. The refrigerant enters the evaporator almost completely in a liquid state and at a very low temperature, which allows it to absorb a large amount of heat from the interior of the vehicle. The system's blower draws the air from the cabin and forces it through the cold coil, allowing the air to return to the interior with a significantly lower temperature. This continuous process maintains a comfortable thermal sensation for the occupants, even under demanding environmental conditions. During this cycle, the refrigerant absorbs heat, evaporates, and changes from a liquid state to a gas state, completing an essential part of the cooling process. This phase change occurs thanks to the design of the evaporator and the low pressure inside it. As a result of the thermal exchange, the air passing through the coil can decrease its temperature, for example, from 23 degrees Celsius, 73 degrees Fahrenheit, to 10 degrees Celsius, 50 degrees Fahrenheit, achieving noticeable cooling in a matter of seconds. Types of evaporators. 1. Serpentine tube evaporator, with fins and without fins. This is one of the oldest designs used in automotive systems and was widely used in the first vehicle air conditioning models. Its structure consists of a copper or aluminum tube arranged in a serpentine shape and surrounded by aluminum fins that increase the heat transfer area. These fins help the heat from the air be absorbed more quickly by the refrigerant flowing inside the tube. The refrigerant must travel through the entire tubing of the serpentine. Its thermal efficiency is limited due to the way the refrigerant flows inside the tube, which may result in lower performance in very hot climates or in larger vehicles that require greater cooling capacity. This type of evaporator was very common in vehicles manufactured between 1970s and 1990s, a period in which vehicle air conditioning systems began to become popular in the automotive industry. 2. Plate and fin evaporator, serpentine-shaped. This evaporator no longer uses tubing with a circular cross-section, but a rectangular one. It is composed of 2 or more parallel plates with internal and external fins arranged in a serpentine shape, which significantly increase the contact area between the refrigerant and the air. Its design allows for more efficient heat exchange, achieving better performance with a relatively compact structure. This type of evaporator was commonly found in many vehicles produced between 1990 and 2005, a time when the industry sought to increase efficiency without significantly increasing the size of the components. 3. Micro-channel evaporator. It does not use a serpentine configuration. Instead, the refrigerant flow passes through several parallel channels, reducing the distance the refrigerant must travel. This modern design uses flat micro-tubes arranged in parallel, allowing the refrigerant to circulate through multiple narrow conduits. Each microchannel increases the contact surface between the refrigerant and the metal, optimizing heat transfer. This evaporator offers high thermal efficiency, reduced size, excellent heat exchange capacity, lower weight which contributes to fuel savings. Modern use. These models have been widely used in automobiles from 2010 onward, especially in compact and next-generation vehicles, where energy efficiency and weight reduction are key factors. Remember that in the video description, you will find the link to access the evaluation of this class, where you can reinforce what you have learned and check your level of understanding. Evaporator temperature. As we saw in the previous class, the evaporator must be kept above 0 degrees Celsius, 32 degrees Fahrenheit, to avoid frost or ice formation, a phenomenon caused by condensation and freezing of moisture in the air. Under normal operating conditions, especially when the engine is idling, The ideal evaporator temperature is 4 degrees Celsius, 39 degrees Fahrenheit. On the low-pressure gauge, we can determine the pressure corresponding to that temperature simply by locating 4 degrees Celsius, 39 degrees Fahrenheit, on the R134A refrigerant scale and reading the resulting pressure value. Some newer vehicles use R1234YF as a replacement for R134A. In that case, to obtain the ideal pressure, the same procedure must be followed, but the gauge must have the temperature scale for R1234YF. Remember that in the video description, you will find the link to access the evaluation of this class, where you can reinforce what you have learned and check your level of understanding. Most common failures of the evaporator. 1. Refrigerant leaks, the most frequent failure. The evaporator may be perforated due to internal corrosion caused by moisture and acids from degraded lubricating oil, external corrosion from dirt, mold, and accumulated bacteria, vehicle vibrations that deteriorate joints or welds. Symptoms: slow refrigerant loss, gradual reduction of cooling, oil stains inside the module, in some cases a sweet or chemical smell inside the cabin, blue gauge pressure lower than normal. 2. External or internal evaporator blockage. This occurs when, due to external blockage, the airflow decreases, or when internal tube blockages affect the refrigerant flow. Dust and dirt on the coil fins. Internal blockages caused by moisture or carbon or metal particle debris. Symptoms: weak airflow even though the blower is working. Evaporator freezing. Noticeable reduction in cooling capacity. Blue gauge pressure lower than normal. 3. Evaporator freezing. Common causes: faulty expansion valve that allows excess refrigerant, insufficient refrigerant charge, damaged evaporator sensor, clogged cabin filter, slow blower or fan. Symptoms: air starts cold but then decreases, ice formation inside the evaporator module, freezing of the low pressure line, blue gauge pressure lower than normal. 4. Bad odors caused by bacteria and fungi. The evaporator remains wet due to condensation, which promotes microorganism growth. Symptoms: musty or moldy odor when turning on the AC, possible irritation in sensitive passengers. Main cause: lack of maintenance or cabin filter replacement. 5. Water leakage inside the vehicle. Condensation may enter the cabin if the drain is clogged or the module box is not properly sealed. Symptoms: water on the passenger side carpet, persistent humidity inside the vehicle. 6. Faulty evaporator temperature sensor or low-pressure switch issues. The function of the thermistor or low-pressure switch is to prevent coil freezing. When it fails, the evaporator may freeze completely or the compressor may shut off prematurely, reducing cooling. 7. Damage or corrosion on the fins, caused by impacts during maintenance, aggressive cleaning products, environmental corrosion over time. Consequences: bent fins, airflow restriction, reduced heat transfer. Symptoms: weak, cold air, poor performance in extreme heat,